Wow, Ray Ozzie saying complexity kills. That's a strong statement. Seems counterintuitive. I mean, sometimes more features, more complexity, right?
Exactly. But that complexity, particularly in software, isn't just about extra lines of code. It's about tangled logic, hard to understand relationships between modules. It makes the whole system harder to plan, build, and test. Imagine a house with so many interconnected pipes and wires. Maintenance is a nightmare. Same with code.
Right. So, what kind of complexity are we talking about?
Well, imagine a function that does 10 different things. That's probably too much. Code should focus on one clear, single responsibility. We use design patterns to manage that kind of thing.
Like what? Give me a real example.
Sure. A function designed to handle user logins should only do that, not also validate email addresses or manage user profiles. Separate functions for those tasks.
But what if a feature needs lots of things? Is that always a bad thing?
Not necessarily. But if not well planned and structured, it can create a maintenance headache. Think solid principles, single responsibility, open-closed, list-off substitution, interface segregation, dependency inversion. Following these is key.
Okay, I get it. So, it's not about avoiding complexity, but about managing it? It seems like refactoring is a key part of that.
Absolutely. Identifying parts of the code that are complex, breaking them down. That's refactoring. And remember, good testing helps expose complex code early in the development process.
So, that testing helps prevent complexity?
Yeah, a robust test suite means you know the boundaries of your code and you can refactor with more confidence knowing the code works as intended. It's not always possible to avoid complexity in every situation. Sometimes there are genuine constraints that mean you have to deal with the complexity, but you should deal with it in the right way.
So, it's like trying to make the house with lots of pipes simpler, not adding more. That makes sense.
Exactly. Avoidance is key.
So, Robert, you're saying cities, these sprawling, complex systems manage to, mostly work because they're essentially modular? Like the water department has its own thing, traffic has its own, and they all kind of interact, but in a controlled way?
Exactly, Andrew. It's about separation of concerns. Different teams focus on different parts, and they can each improve without needing to know the intricate details of the entire system. That's a big lesson.
But in software, isn't that harder? It's all one big, code base.
You're right. It's not always easy. And software projects often suffer from the opposite of that modularity. Imagine a monolith, everything jammed together.
So, how do you build modularity in software then? It feels like a whole different set of rules, right?
Well, clean code at the function level helps, but it's not enough. We need to think about the system as a whole. We need to design modules, not just functions.
So, modularity isn't just about functions within code, but the structure of the code base itself?
Exactly. Think about libraries and APIs. They're essentially modular components that other code can utilize. A good system design often involves carefully crafting those interactions.
Like maybe designing reusable components that can be swapped in and out, with clear defined inputs and outputs. That's like the water department in a city, handling its own input and output.
Exactly. And, you could even use a design pattern for this.
A design pattern for this, interesting. So, what are the pitfalls of not doing that?
Well, projects can become hard to maintain, and you often end up with a ball of mud. Suddenly, a single change in one module affects others in unpredictable ways.
Wow, that's like a ripple effect, but way worse in software.
Absolutely. And there's more to it. Abstraction. Hide unnecessary details and expose only what's essential. That makes the code easier to understand and change.
So, it's like a layered approach to code, like building up from a simple component to a more complex system.
Exactly. It all starts with this, with clear structure and intent. And that, in turn, will lead to cleaner code as a whole, rather than just at the micro level.
So what about the challenges in applying that to, say, a large web application project?
That's a good question. We have to think about how to break the system down, manage dependencies, and coordinate different teams working on different modules.
Fascinating. This is helping me see the big picture of software development. Thanks, Robert. So, Rober, you're saying we should totally isolate the construction phase from the application logic?
Exactly. Think of it like building a house. You build the foundation, frame and walls construction, then move in and furnish it application. The two aren't intertwined.
Got it. So, no more shared variables or methods.
Exactly. The application just gets the house, ready to go. No need to know how it was built.
Okay, that sounds elegant. But in a larger project, how do you manage complexity?
You use modules, functions, and classes. Imagine a factory that builds your house components.
A factory? Like a design pattern?
Precisely. The factory handles the creation of objects, and the application just asks for them. Very clean.
Makes sense. But what if, there's a hidden dependency or a subtle error in the construction phase?
Good point. Testing is crucial, and you design your construction phase to be testable on its own. This allows for independent quality assurance. There are many unit testing frameworks for that.
So, it's about having clean interfaces then.
Yes, totally, and ideally you have well-defined interfaces for the object construction.
I see. This seems like a big win for maintainability.
It definitely is. You can change the construction method without affecting the application. It's easier to scale, and less prone to errors.
Makes sense. Is there a real-world example you can think of where this helps solve a problem?
Sure, imagine a large e-commerce platform. You can build the payment processing components independently.
Wow, that's a huge improvement.
And the application doesn't need to care. Just asks for a working payment module. The factory handles all the nitty-gritty.
Fascinating, Rober. Thanks for clarifying this.
You're welcome. It's all about separating concerns and building robust, maintainable code.
Totally. This makes a ton of sense. So, Robert, you were talking about factory patterns. This seems like a powerful tool for building robust apps, but can you give us a simple example?
Sure, imagine an order processing system. You don't want your main order processing logic cluttered with code for creating different types of line items.
Right? A factory handles that?
Exactly. The factory handles the specifics of each line item type, like a product or a service. Your application code just tells the factory, create a product line item, and the factory takes care of it.
But doesn't that create extra layers of abstraction?
Well, extra abstraction can be a good thing. It makes your code more organized and maintainable. If you need to change how a product line item is created, you only change the factory, not your main order processing code. Less chance of bugs.
Makes sense. Is there a downside?
Sometimes, very simple scenarios might be over-engineered with a factory pattern. It depends on the size of the project.
So, how do you know when to use it?
When you start having multiple, maybe different, types of items being generated. Imagine generating product, service, or tax items for an order. Then it's worth the extra layer of abstraction.
A real-world example?
Think of an e-commerce site. Different kinds of products might have different properties. Using factories would make updating line item generation more manageable if you introduce new items.
Okay, that helps. So, it's about modularity and preventing code tangling?
Exactly. Decoupling your code with factories promotes code maintainability and efficiency.
Interesting. What about performance? Won't these additional layers slow things down?
Well, in simple cases, yes, slightly. But in cases with larger systems and potentially more complex object constructions, the performance gains from maintainability generally outweigh the minor overhead.
That makes a lot of sense. Thanks, Robert.
You're welcome. Let's talk more about when to avoid factory patterns next time.
So, Robert, you're saying we can build software systems incrementally? Like just start small and add features as we go?
Exactly. Think of cities. Roads get wider, buildings get taller. It's not always the perfect, initial design, but it works.
But doesn't that lead to problems? Like in a software system, isn't there a risk of things getting messy?
Absolutely, but that's where separation of concerns comes in. It's like building with modular blocks. You can change one part without affecting the whole thing.
Okay, separation of concerns. Can you give me a concrete example?
Sure. Old EJB architectures didn't do that well. Imagine a bank system. Everything was tightly coupled. Making changes was difficult, and testing became a nightmare.
Why? Tight coupling is problematic. Can you expand?
The code was stuck tightly to the EJB container. Everything had to be tailored to the container's way of working. Meaning, if the container changed, your code needed to be modified too.
So, if you change a method in one component, it might affect others? And testing becomes hard?
Exactly. You can't test a single part in isolation.
So, how do you fix that? How do you separate concerns?
Design your system with well-defined modules. Have clear interfaces between them. It's all about loose coupling.
That makes sense. So, this concept of incremental agility applies to other things besides software, right?
Absolutely. Any complex system that needs to adapt over time benefits. Think of urban planning, or even biological systems.
So, is this always a better approach than planning everything out up front?
Well, it depends. You still need a basic understanding of your requirements, but it allows for flexibility in a way that's not possible with a rigid structure.
Right. You don't have to foresee everything from the beginning. Makes sense.
Exactly. It's about building the right thing, not necessarily the perfect thing from the start.
So, that means it's not a one-size-fits-all approach, right?
No. It's about choosing the right tool for the job.
Thanks, Robert. This was really helpful.
You're welcome.
Hey, Robert, we've been talking about writing clean, maintainable code. So, these cross-cutting concerns, what exactly are they?
Imagine you need to persist data across a bunch of different classes. You need to do it consistently, with the same database, the same naming conventions. That's a cross-cutting concern. It's something that affects many parts of the application, but isn't really tied to any one object in particular.
So, it's like a hidden thread running through the program?
Exactly. And that's why it can get messy when your codebase gets large. You have to sprinkle persistence code all over the place, which makes it harder to maintain.
EJB2 tried to address that, right?
Yeah, EJB2 moved some of that declaration stuff into deployment descriptors, which was a step forward. But it still had its limitations.
So, what's AOP? How does it help?
AOP lets you modularize those cross-cutting concerns, like persistence. You make reusable components called aspects that modify the behavior of parts of your system at specific points.
So, you specify where in the code you want the behavior to change?
Exactly. You define the points of insertion, the points of influence. A join point is the technical term. It's all declarative. You don't have to change the code directly. That's cleaner, right?
That's cool. So you use aspects to control how these concerns are handled?
Absolutely. You can specify which objects and attributes are to be persisted, which ones are secured, and so on. The aspect framework then handles the details behind the scenes, making it cleaner and less error-prone.
So, you can use AOP in any codebase, right?
Well, it's not always the best solution. It can introduce complexity into projects without much benefit, especially in simple applications. But for larger apps, it's a great way to make things more maintainable. Also, it's good for supporting changes to data persistence strategies.
Wow, that sounds powerful. Can you give me a quick example? Like, how you tell AOP to persist this class or that field?
Sure. You declare within an aspect which classes need persistence and then delegate the persistence to a framework. Think of it as marking specific sections of your code.
Got it. So, AOP lets you handle concerns in a more modular way.
Exactly, keeping your core domain logic clean.
Thanks, Robert. Robert, we've been discussing AOP, and now you're talking about pure Java approaches. Can you break that down for me?
Sure. Pure Java AOP frameworks, like Springs, use Java proxies to implement aspects without needing Aspect-J. They let you focus on your core business logic, POJOs, and delegate the infrastructure details to the framework.
So, no Aspect-J? That's a big simplification, isn't it? How do these frameworks manage that?
Yes, it's a powerful simplification. The framework manages the proxies dynamically, often using bytecode manipulation. It's all hidden behind declarative configuration.
Declarative configuration? Can you give me a simple example?
Sure. Spring uses XML files to define dependencies. You describe what objects you need and how they relate, and the framework handles the wiring.
That sounds interesting. How does this impact testability?
testability skyrockets. You can isolate your POJOs from the framework-specific plumbing. Testing becomes much cleaner and easier.
Wow. So, are there any trade-offs?
Well, XML configurations can be verbose, but the trade-off is worth it for maintainability. Annotations exist too, and they're a good compromise.
Makes sense. But what about performance? Doesn't using proxies add overhead?
In many cases, the overhead is negligible. The frameworks are optimized to handle this well.
You mentioned EJB3. How does that fit into this?
EJB3 largely adopted Spring's model, using annotations to handle cross-cutting concerns. It shows how important the approach became.
Interesting. So, pure Java AOP is essentially a cleaner, more maintainable way to build applications.
Yes, and the decoupling is huge. This is a paradigm shift from earlier approaches.
Thanks, Robert. This clarifies so much.
My pleasure.
So, Robert, we've talked about various strategies for clean code, like solid principles and dependency injection. Now, let's talk about aspect-oriented programming. What's the deal with Aspect-J?
Aspect-J is a powerful extension of Java. It's a sophisticated approach to separating concerns.
Can you give us a quick comparison to simpler methods like Spring AOP?
Spring AOP is great for most cases. Think about 80 to 90% of projects where aspects are useful. But Aspect-J offers more features for handling cross-cutting concerns.
So, what exactly are cross-cutting concerns?
They are tasks that affect multiple parts of your codebase. Things like logging, security, or performance monitoring are often cross-cutting. Aspect-J handles them in a modular way, which is why they're more powerful.
Is it more useful to developers who are super familiar with code?
It definitely has a steeper learning curve than Spring AOP. The syntax is different, and you have new concepts to learn, which is where the annotation-based system helps a ton.
Are there real-world examples where Aspect-J really shines?
Absolutely. Imagine a system with lots of classes needing logging. Instead of adding logging code to every method, you can use an aspect to log all calls.
That makes it easier for maintenance and readability.
Exactly. Plus, if security rules change, you can easily modify the aspect instead of changing every class that interacts with the data.
Does that mean it's just for massive projects?
No, even moderate-sized projects can benefit in terms of organization.
So, Aspect-J, while powerful, isn't necessary for everyone?
Absolutely not. Spring AOP and other approaches are often perfectly adequate.
Thanks, Robert, for that great explanation on Aspect-J. It certainly helps in understanding the value trade-offs.
You're welcome.
Robert, you've talked about the importance of clean code, but now you're talking about designing the system architecture in a more agile way?
Yeah, Andrew, I think you're on the right track. You gotta be able to adjust as the system grows. You know, BDUF, big design up front? Not really a good idea.
Not a good idea? Why?
Well, it locks you into a specific architecture early on. It gets really hard to change course later as you gather new requirements.
So you're saying, start simple, then build up?
Exactly. Separate the concerns, and build your domains independently. Using POJOs, plain old Java objects helps, decoupling your concerns and makes them testable. Then you use aspects or aspect-like tools to integrate those domains.
Aspects? Could you give me a real-world analogy?
Imagine building a house. You don't need to design the entire electrical system first, before you start with the foundations. You can figure out the specifics as you go.
But what if you get the wiring wrong early on?
You see, that's where it's different in software. If you have it correctly decoupled, you can swap a wiring system for a more sophisticated one later without major problems. The separation of concerns helps in mitigating the complexity of changes.
That makes sense. So, you're saying it's okay to be a bit rudderless in the beginning?
Not exactly rudderless. You have an idea of the scope, but you can always change it.
But how do you deal with the trade-offs between speed and robust architecture?
You prioritize the core functionality initially and then add layers as needed. Don't over-engineer the early parts, and use this test-driven approach to add complexity gradually. Use aspects to seamlessly connect.
That sounds like a good balance. Thanks, Robert. So a simple and well-decoupled architecture is the key?
Exactly. This is how large web applications can achieve high performance and availability. You can just keep scaling as needed.
It's a fresh way of thinking. Thanks for the insights.
You're welcome, Andrew. Now tell me, what's your next question?
Hey Robert, great to have you back. We were talking about clean code, and now it seems we're getting into standards. How do standards relate to writing clean code?
Well, Andrew, standards can be fantastic. They offer a proven path, reusable components, and a shared vocabulary. But sometimes they can be overkill.
Overkill? Can you give an example?
Sure. Imagine a team using a super complex framework for a simple web app. That might be a standard, but it's probably overkill. It doesn't offer any real value and makes the code harder to maintain.
So, you're saying it's about the value added, not just following the standard?
Precisely. Is the standard really helping you write clean, maintainable code, or is it just bloating the project?
So, how do we know if a standard actually adds value?
You've got to measure it. Look at the project requirements, the team's skill set, and the overall complexity. Does the standard improve efficiency? Does it reduce errors? Does it make the code more readable and maintainable? If not, it's probably adding unnecessary complexity.
So, the standard has to be specific to the project and not a one-size-fits-all solution?
Exactly. Think about it. Different tools for different jobs, right? Clean code standards should act similarly.
Right. I see. Okay. So how does a developer navigate this?
They need to evaluate the cost/benefit, Assess the standard against the specific needs of the project. Often the clean solution is to avoid or modify the standard. It's about being resourceful.
A lot to consider. One last question. Any personal experience with a standard that ultimately didn't add value to the project?
Definitely. Once, a team adopted a very popular, but large framework for a simple application. It resulted in a huge overhead, slow development time, and ultimately code that was hard to understand.
Wow. Thanks for the great insight. I think we've covered a lot today. Robert, we've been talking about writing clean, maintainable code. Now, you're saying there's another tool in the toolbox, domain-specific languages, or DSLs.
Exactly. Think of it like a specialized vocabulary for a specific job. Building construction has its own language, right? There are specific terms and ways of describing things that make sense within the industry.
So, a DSL is like a mini language for a particular task?
Yes, a small specialized scripting language or API that sits inside a standard language like Java, Python, or JavaScript. Instead of writing complex, multi-layered code, you write a set of instructions that read like a description. It's essentially giving the code more prose clarity.
How does this improve communication in software projects?
Think of the communication gap between the software developer and the domain expert, person designing the software. Using a DSL helps them to understand each other. The developer speaks the same language as the expert, minimizing the risk of misinterpretation. It's like having a translator.
But wouldn't this create another learning curve for developers?
Potentially, but the payoff is big. You're raising the abstraction level, allowing developers to focus on the bigger picture instead of getting lost in the details. It's like switching from coding to writing specs, a clear, understandable description of the function.
Can you give an example?
Sure, JMock, a Java API, is a DSL. It lets you define tests in a more straightforward way compared to using traditional object-oriented Java methods.
So, DSLs are like a shortcut for writing readable code?
Exactly, a concise and focused language that communicates directly to the problem domain.
Do you have any experience with it, where it really paid off?
Yes, in financial modeling, it drastically shortened the time to development and reduced errors caused by misinterpretations.
So what are the challenges? Is it always better?
It's not a silver bullet. Maintenance can be a factor. But if it streamlines the development process, it can be a worthwhile investment.
Fascinating. So, Robert, you're saying clean architecture isn't just about individual functions, but the overall system design too?
Exactly, Andrew. A poorly designed system, like an invasive architecture, can quickly strangle your domain logic.
How so? Can you give a quick example?
Sure. Imagine a system where all your business logic is tangled up with infrastructure concerns. Think lots of dependencies, spaghetti code, and hard-coded paths.
Okay, that makes sense. So, what's a better alternative?
You need a clear separation. POJOs, plain old Java objects, are crucial for keeping your domain logic pure and independent.
And these aspect-like mechanisms?
They're like modular additions. Logging, security, caching, those things get implemented without modifying your core domain.
So you're saying no more monkey patching or extensive use of decorators?
Exactly, simpler is better, if it still meets requirements.
Makes sense. But in the real world, isn't a clear separation sometimes hard?
It's more like a design trade-off. Sometimes, you gotta find that balance.
Interesting. How does this connect to TDD?
TDD forces you to think about the domain first, and you can apply this architectural clean structure to the TDD process. You build a solid foundation, and the tests themselves help to keep the architecture clean.
So, is this always the best approach?
Not necessarily. Sometimes, a slightly more complex architecture is unavoidable. It depends on the project's complexity, but the key is to know when the extra complexity becomes a liability.
That makes a lot of sense. So, modularity is essential?
Yes, modularity and simplicity.
Thanks, Rober. That was incredibly helpful.
You're welcome, Andrew. It's all about clean code, well-structured systems, and keeping those complexities separate from your domain logic.
Good point. Thanks a lot.